If you have already learned control systems, you might have come across integrator, and we must have often heard people say that when we give a constant input to this integrator, we get a ramp output. And when we give a ramp input to this integrator, we get a parabolic output, and it goes on, continues. So why does this behave this way, or how is the mechanism inside the integrator as a black box, right? As a generic integrator, regardless of which domain it's being implemented on, just as a black box, which behavior of integrator leads to this kind of input giving this kind of output, and this kind of input giving this kind of output. Or to be in exact mathematical terms, you might have come across situations where if you give some constant k as input, you will get kx as output, and if you give some kx as input, then you will get kx square by 2 as output. So why is this happening basically, and how is this happening? That's the thing which we are going to focus on this video. Now I have an integrator. I'm going to give an input signal to it, and then I'm going to continue my explanation. My first input signal is going to be a constant signal, or in proper conditions we can say it's a step signal. So here my signal is plotted across time in the x-axis, and this is the amplitude of the input signal. This is the input signal's amplitude. So in the 0th instant of time, it is having a value of 1, and it is constantly having a value of 1 until the first second, and this time is in seconds. Okay, until the first second it is having this. So what my integrator does is it computes the area under the curve which is given as input to this. This is my curve right now. So what is the area under this curve until this point? Up to whatever point the curve is present, until that point, what is the area under that curve? That's the thing that my integrator computes. So what is the area here? It's 1 into 1, which is 1. So when I talk about output of the integrator, you have to understand x-axis is time and y-axis is area. Y-axis is area. So I am measuring the area here in this region. In this region, my area is 1 into 1, which is 1. So I am plotting the area here, the y-axis. So at the first second, my area is having value 1. So I am plotting it here, right? And the signal continues to be constant for the next 1 second also. Now what is my curve? My curve is not just this line. As I said earlier, integrator will give the output as the area under the curve until that point of time. So until this point of time, this is my whole curve. Now what is the area under this curve? Its breadth is 1 and length is 2. So 2 into 1, which is 2 square units. Now I'm plotting this 2 square units here. So this basically the unit here is square units, right? So at the second time is equal to 2 seconds, what is my total area? It's 2 square units. So I'll plot it here. Now we can get an idea. Now if you go on providing, if you keep providing that input again, that is, it's consistently being constant. So at the third second, what is the area under this total curve? It is 3. 3 into 1 is 3. Now at the third second, my area is 3. Now if you plot all this, if you plot all this, what is it? This is a ramp. So when I am giving a constant input, I am getting a ramp output. The point that we need to understand here is this is the output of integrator. Now moving on, I have another example in which my input is going to be a ramp. This is the input amplitude. This whole signal is going to pass through the integrator and we are going to observe the output. Now we have at the 0th second, the value is 0. At the first second, my value is 1. So my signal, input signal is like this. Right. Now, at the first second, what is the output of the integrator? That is, what is my area in square units? That's the question. So what is the area under this curve? The area under this curve is basically looking like a triangle. So we can use half base into height. So half into base into height is 0.5. So here you will have 0.5. At the first second, my area is 0.5. So at the first second, my area is 0.5. This is the first data point. Next, the curve continues to be increasing. It's a ramp, so it continues to increase. And at the second, my input value is 2. Now, what is the area under this whole curve? Will be the output of the integrator. What is the area under this whole curve? This is again a rectangle, so we have half times base times height, which is 2 square units. So at the second, that is when t is equal to 2 seconds, my output is 2. In the third second, what will be my output? It will be the area under this whole curve. So it's half times base times height, which is 9 upon 2, which is 4.5. So at the third second, my value will be 4.5. If you connect all these points together, you will get a parabola. And this is a ramp. What is the point I'm trying to convey here again? This area is your integrator's output. Now let us assume that I have to implement this integrator in some domain. So I take a capacitor. And I'm going to charge this capacitor by a current source. This is my current source. I'm going to charge my capacitor with this current source. So this will be my circuit. And as the current gets deposited here, the voltage across this capacitor keeps on increasing. If this current is constantly 1 ampere, then the voltage will be increasing. This is the voltage across the capacitor. This will be increasing linearly. Why? Because the input is current and the output is voltage. Now we know that in a capacitor, the current and voltage are related in two ways. First is when your output is a voltage and input is current, the relation is like this. And if your input is voltage and your output is current, then it is related like this. We are observing the voltage across the capacitor. Now This will make more sense if this current source is actually not a fixed current source, but the magnitude of this current source is dependent on some error which is occurring between a reference signal and an actual signal. If this is able to control the magnitude of this current, then the difference between this reference and actual will decide the magnitude of this current, whether this should be 1 ampere or 0.5 ampere, and so on. So this is nothing but a transconductance amplifier. If this is your capacitor, then this is your transconductance amplifier. This scenario was discussed as a part of the system in the previous video.